High above us in the vast expanse of space shines a celestial beacon that has captivated humanity since the dawn of time. The sun. It's a giant ball of burning gas, a cosmic furnace that fuels life on Earth. More than just a source of light and warmth, the sun is the gravitational anchor of our solar system, holding planets, asteroids, and comets in its sway. For millennia, humans have gazed upon the sun with a mixture of awe and reverence. Ancient civilizations worshipped it as a deity, recognizing its power over the seasons and the cycles of life. The Egyptians had Ra, the sun god who sailed across the sky each day, while the Greeks honored Helios, who drove a chariot of fire across the heavens. The sun's influence on Earth is profound. Its energy, in the form of light and heat, is the engine that drives our planet's climate and weather patterns. Through the process of photosynthesis, plants capture the sun's energy, converting it into the food that sustains nearly all life on Earth. But the sun is more than just a benevolent provider. It's also a celestial powerhouse capable of unleashing incredible bursts of energy. Solar flares, coronal mass ejections, and other phenomena remind us of its raw power and the importance of understanding its behavior. To truly grasp the significance of the sun, we must first consider its staggering size. Our star is a true giant, dwarfing the Earth and all the other planets in our solar system combined. With a diameter of roughly 865,000 miles, over 100 Earths could fit across its face. And it's not just the sun's size that's impressive. Its mass is equally awe-inspiring, containing over 99.8% of the total mass of our solar system. The sun exerts a gravitational pull that keeps all the planets, including our own, locked in orbit. To put the sun's size into perspective, imagine shrinking it down to the size of a basketball. On this scale, the Earth would be a mere speck, about the size of a pinhead, orbiting at a distance of about 25 meters. The vast distances between objects in space become strikingly clear when we consider these relative sizes. But despite its immense size and mass, the sun is not the largest or most massive star in the universe, not by a long shot. It's classified as a yellow dwarf star, a relatively common type in our galaxy, the Milky Way. The sun's energy, radiating outward in all directions, is the lifeblood of our solar system. It bathes the Earth in light and warmth, making our planet habitable. This energy comes from the sun's core, where temperatures and pressures are so extreme that nuclear fusion takes place. Deep within the sun's core, hydrogen atoms are constantly colliding and fusing together, forming helium and releasing tremendous amounts of energy in the process. This energy then slowly makes its way outward, eventually escaping into space as sunlight. The sun's energy drives Earth's climate system. It warms the atmosphere, oceans, and land, creating the temperature gradients that drive winds and ocean currents. These, in turn, distribute heat around the planet, influencing weather patterns and shaping the Earth's diverse ecosystems. The sun's energy is also essential for life itself. Plants, algae, and some bacteria use sunlight to carry out photosynthesis, converting light energy into chemical energy in the form of sugars. This process forms the base of the food chain, providing energy for all other life on Earth. For centuries, scientists have sought to unravel the mysteries of the sun. Early astronomers, limited by the technology of their time, could only observe the sun's surface, tracking sunspots and solar eclipses. But with the advent of telescopes and other scientific instruments, our understanding of the sun began to deepen. Today, we study the sun using a fleet of sophisticated spacecraft equipped with instruments capable of observing across the entire electromagnetic spectrum, from radio waves to gamma rays. These spacecraft provide us with unprecedented views of the sun's surface, its atmosphere, and its magnetic field. We've learned that the sun is a dynamic and complex object, far more than just a ball of burning gas. It has a layered structure with a core, radiative and convective zones, and an atmosphere composed of the Photosphere, Chromosphere, and Corona. Each layer plays a crucial role in the sun's behavior and its influence on the solar system. Our exploration of the sun is far from over. Many questions remain unanswered, such as the precise mechanisms driving the sun's 11-year cycle of activity, the nature of the solar wind, and the long-term fate of our star. By continuing to study the sun, we hope to unlock its secrets and gain a deeper understanding of our place in the universe. Our Sun, despite its grandeur within our solar system, occupies a relatively humble abode in the vast expanse of the Milky Way galaxy. Imagine the Milky Way as a sprawling city of stars, a cosmic metropolis teeming with celestial objects. Within this city, our Sun resides in a quiet suburban neighborhood, far from the bustling galactic center. We're situated about 2/3 of the way out from the galactic center, in one of the Milky Way's spiral arms, gracefully swirling around the core like a Ferris wheel rider. From our vantage point, we look inward towards a dense, luminous bulge of stars, shrouded in interstellar dust and gas. The Sun, along with its planetary entourage, orbits the galactic center at a speed of roughly 500,000 miles per hour. Even at this breakneck pace, it takes us about 230 million years to complete one orbit around the Milky Way, a journey known as a galactic year. The Sun's location in this relatively peaceful region of the galaxy is thought to be crucial for the development of life on Earth. The galactic center, while visually stunning, is a turbulent and chaotic place, bombarded by intense radiation and subject to gravitational disruptions from densely packed stars and black holes. The Sun's story begins billions of years ago, in a cold, dark cloud of interstellar gas and dust known as a nebula. These nebulae are the birthplaces of stars, cosmic nurseries where gravity slowly draws matter together over eons. Imagine this nebula as a vast, diffuse cloud, much larger than our solar system is today. Within this cloud, random eddies and turbulent motions caused by distant supernova explosions or the gravitational pull of passing stars created regions of slightly higher density. Over time, gravity amplified these density differences, pulling more and more gas and dust towards these denser regions. As these regions collapsed inward, they spun faster and faster, like a figure skater pulling their arms in during a spin. The infalling material, drawn in by the relentless pull of gravity, converted its gravitational potential energy into heat, causing the central region of this collapsing cloud to glow ever brighter. This glowing core would eventually ignite as a star, our Sun. Once the Sun's core reached a critical temperature and pressure, nuclear fusion ignited, marking the beginning of its life as a star. Hydrogen atoms, the most abundant element in the universe, were forced together under immense pressure, fusing to form helium and releasing tremendous amounts of energy. This energy, radiating outward from the core, created an outward pressure that balanced the inward pull of gravity. The Sun settled into a state of hydrostatic equilibrium, a delicate balance between these opposing forces, and entered a long, stable period known as the main sequence. Our Sun has been in this main sequence phase for about 4.6 billion years, and it's expected to remain so for another 5 billion years or more. During this phase, the Sun's size, temperature, and luminosity remain relatively constant, providing a stable source of energy for the developing solar system. Throughout its main sequence lifetime, the Sun gradually converts hydrogen to helium in its core. This process, while incredibly efficient, is not infinite. As the Sun ages, the hydrogen fuel in its core slowly depletes, setting the stage for dramatic changes in its later life. Billions of years from now, the Sun will reach a pivotal turning point in its life cycle. As the hydrogen fuel in its core dwindles, the outward pressure generated by nuclear fusion will diminish. Gravity, always present, will begin to gain the upper hand. The Sun's core, starved of hydrogen fuel, will contract under its own weight, causing its temperature and pressure to soar. This intense heat will ignite hydrogen fusion in a shell surrounding the core, while the core itself will continue to contract and heat up. The energy released by this shell fusion will be far greater than the Sun's current energy output, causing its outer layers to expand dramatically. The Sun will swell to an enormous size, engulfing the orbits of Mercury, Venus, and possibly even Earth. Our once yellow dwarf star will transform into a red giant. This red giant phase will last for a few 100 million years. During this time, the Sun's luminosity will increase thousands of times, bathing the inner solar system in a fiery glow. The Earth, if spared complete engulfment, will be a scorched and barren wasteland, its oceans long boiled away. As the Sun continues to evolve as a red giant, its core will reach temperatures and pressures sufficient to ignite the fusion of helium into carbon and oxygen. This helium-burning phase will be relatively short-lived, lasting for a few 100 million years at most. Once the helium in the core is exhausted, the sun will enter a period of instability. The core will contract again, while the outer layers pulsate violently, shedding material into space in a series of dramatic outbursts. These ejected layers of gas and dust, illuminated by the dying star's radiation, will form a breathtaking cosmic spectacle known as a planetary nebula. These nebulae, despite their name, have nothing to do with planets. They were simply named for their resemblance to faint, fuzzy planets when observed through early telescopes. As the sun sheds its outer layers, its core will be exposed, a dense, hot object known as a white dwarf. This white dwarf, composed primarily of carbon and oxygen, will be incredibly dense, packing a mass comparable to the sun's current mass into a volume roughly the size of Earth. The white dwarf stage marks the final chapter in the sun's life story. No longer able to sustain nuclear fusion, the white dwarf will slowly cool down over billions of years, radiating away its residual heat into space. As the white dwarf cools, its luminosity will gradually fade. It will transition from a white-hot ember to a yellow, then orange, and finally a red-hot ember, eventually fading from view entirely. This cooling process is incredibly slow, taking trillions of years. The white dwarf remnant of our sun will eventually become a black dwarf, a cold, dark object no longer emitting any significant heat or light. This black dwarf, composed of the ashes of our once mighty star, will continue to drift through the galaxy, a silent testament to the life and death of a star. The sun's life cycle, from its birth in a nebula to its demise as a black dwarf, is a story of cosmic transformation, a testament to the power of gravity, nuclear fusion, and the vastness of time. The word sun, simple yet profound, carries a history stretching back to ancient tongues. Its roots lie in Proto-Germanic so well, connecting the sun to light and vision. Across cultures, the word sun evolved from Sonne, son, zon, so, soleil, reflecting our shared wonder and the enduring legacy of the sun in language. The sun has inspired awe since the dawn of civilization, worshipped as a powerful deity across cultures. In Egypt, Ra sailed the sky, bringing light and life. The Greeks honored Helios, charioteer of the heavens. In the Americas, the Aztecs honored Tanasha, and Incas revered sun gods as the source of all energy. These deities remind us of the sun's vital role in life. The sun has shaped human culture for millennia, inspiring art, myth, and meaning. From ancient cave paintings to modern cinema, its symbolism has evolved, representing life, power, and hope across civilizations. Even today, the sun captivates us, fueling creativity and connecting us to our shared cosmic story. Our sun is a typical yellow dwarf, one among billions in the Milky Way. While it dominates our solar system, it's just an ordinary star, shining steadily for billions of years and providing the stability needed for life. The sun's mass equals about 333,000 Earths, anchoring the solar system with its gravity. Its brightness outshines all human energy use, and its surface blazes at nearly 6,000 degrees Celsius, while the core reaches 15 million degrees, fueling nuclear fusion. These properties define the sun's power and its vital role in our existence. Astronomers classify the sun as a G-type main sequence star, a yellow dwarf. It's middle-aged, steadily fusing hydrogen into helium, and its stability has allowed life to flourish on Earth. This phase will last billions more years, making the sun a reliable cosmic neighbor. Deep in the sun's core, nuclear fusion fuses hydrogen into helium, releasing immense energy. Extreme heat and pressure overcome atomic repulsion, allowing the strong nuclear force to bind protons together. This chain reaction powers the sun's light and heat, sustaining life on Earth. The sun is mostly hydrogen and helium, with trace heavier elements forged in earlier stars. These elements shape the sun's behavior and link it to the universe's ongoing evolution. Our star's composition is a cosmic legacy, connecting us to generations of stars before it. Scientists use helioseismology and neutrino detection to study the sun's hidden layers. Sound waves and elusive particles reveal the sun's internal structure, temperature, and composition. These tools let us explore the sun's depths without ever leaving Earth. The sun's core is a dense, superheated plasma where nuclear fusion occurs. Temperatures soar to 15 million degrees Celsius, creating the energy that powers the sun. Gamma rays born here begin a long journey outward, fueling all solar activity. Surrounding the core, the radiative zone slowly transfers energy outward via photon diffusion. Photons bounce through dense plasma, losing energy and shifting wavelength as they go. This process takes thousands of years, moving energy toward the sun's surface. The tachocline is a thin, turbulent layer, where the sun's rotation changes dramatically. It's a hotspot for magnetic activity, crucial to the sun's magnetic field and solar cycles. Though still mysterious, it's key to understanding the sun's dynamic behavior. In the convective zone, hot plasma rises and cools, creating a churning, boiling surface. This motion shapes the sun's granulated appearance and helps generate its magnetic field. The interplay of convection and magnetism drives solar activity, impacting Earth in profound ways. Finally, we reach the sun's visible surface, the photosphere, a thin layer of plasma that emits the light we see from Earth. Imagine a shimmering curtain of light, a cosmic tapestry woven from countless photons escaping from the sun's interior. The photosphere is our window into the sun's depths, revealing its ever-changing features and hinting at the dynamic processes occurring beneath. The photosphere's temperature, about 5,800 degrees Celsius or 10,000 degrees Fahrenheit, is cool enough for electrons to recombine with atomic nuclei, forming neutral atoms and allowing photons to escape into space without being immediately reabsorbed. This is why the photosphere appears opaque to us, as photons can finally travel freely after their long journey from the sun's core. The photosphere is not a smooth, uniform surface, but rather a turbulent, ever-changing landscape. The most prominent features on the photosphere are sunspots, dark, cooler regions caused by intense magnetic activity that inhibits convection, reducing the energy transport from below. Sunspots appear dark in contrast to the surrounding photosphere because they are cooler, but they are still incredibly hot, with temperatures around 3,800 degrees Celsius or 6,800 degrees Fahrenheit. Sunspots vary in size and shape, and their number and distribution on the sun's surface change over an 11-year cycle, driven by the sun's magnetic dynamo. Beyond the photosphere lies the sun's outer atmosphere, where temperatures rise and densities fall. The sun's magnetic field shapes plasma into loops, arches, and streamers. The chromosphere glows red during eclipses, while the corona, visible in ultraviolet and X-rays, extends millions of kilometers into space. The corona's extreme heat and dynamic structures are powered by the sun's magnetic energy, driving solar flares and eruptions. Deep within the sun's core, nuclear fusion powers our star. Here, unimaginable temperatures and pressures force hydrogen nuclei to collide, overcoming their natural repulsion. The strong nuclear force binds these protons together, releasing tremendous energy and forming new atomic nuclei, fueling the sun's brilliance and sustaining life on Earth. Deep in the sun's core, hydrogen fuses into helium, releasing energy as powerful gamma rays. These gamma rays scatter through dense solar plasma, losing energy and shifting to longer wavelengths. After thousands of years, they emerge as visible light at the sun's surface. This light then travels through space, illuminating and warming our solar system. The energy born in the sun's core doesn't beam straight out. Instead, it takes a long, winding journey through dense layers, bouncing like pinballs in the radiative zone. Once photons reach the convective zone, hot plasma carries them upward, churning and bubbling toward the surface. Here, energy escapes in weeks, not millennia, finally reaching the sun's surface and beyond. The sun bathes Earth in radiant energy, warming our planet and sustaining life. This energy isn't spread evenly. Places near the equator receive more than the poles. The balance between incoming sunlight and outgoing heat shapes our climate. Even small changes to this balance can have profound impacts on Earth and all its life. Beneath the sun's blazing surface lies a realm of intense magnetic forces, shaping its behavior and influencing the solar system. The sun's magnetic field, generated by churning plasma, creates a complex network of field lines. These lines thread through the sun and extend into space, driving dramatic events like solar flares and sunspots. Understanding this restless giant is crucial for predicting its impact on Earth. Gazing upon the sun's blindingly bright surface, one might imagine a uniform, featureless sphere of incandescent gas. However, a closer look reveals a dynamic and ever-changing landscape, marked by dark, irregularly shaped blemishes known as sunspots. These intriguing features, visible from Earth with proper eye protection, offer a glimpse into the sun's hidden magnetic realm. Sunspots appear dark, not because they are inherently less bright, but because they are cooler than their surroundings. They form in regions of intense magnetic activity, where strong magnetic fields, generated by the sun's internal dynamo, rise up from the convective zone and pierce through the photosphere, the sun's visible surface. These magnetic fields, much stronger than the surrounding solar magnetic field, suppress the normal convective flow of heat from the sun's interior, creating localized cool spots on the photosphere. Sunspots can vary in size, from tiny pores barely visible through a telescope, to behemoths larger than the Earth itself. Sunspots are not merely cosmetic blemishes. They are dynamic and often volatile features that can unleash powerful bursts of energy in the form of solar flares and coronal mass ejections. By studying sunspots, their evolution, and their magnetic properties, scientists can gain insights into the sun's internal dynamo, its 11-year cycle of activity, and the potential impacts of space weather on Earth. The sun, despite its seemingly constant presence in our sky, is not a static object. It actually pulsates with a rhythmic heartbeat, a cycle of activity that waxes and wanes over an average period of 11 years. This ebb and flow of solar activity, known as the solar cycle, is driven by the sun's internal dynamo. It's the complex interplay of its rotation, convection, and magnetic fields. Imagine the sun's magnetic field as a giant rubber band, constantly being stretched and twisted by the sun's rotation and the churning motions of its plasma. As the magnetic field lines become increasingly tangled and distorted, they store energy, rather like a wound-up spring, until they reach a breaking point. At the peak of the solar cycle, known as solar maximum, sunspots are abundant, often appearing in groups and covering a significant portion of the sun's surface. Solar flares and coronal mass ejections are more frequent and intense during this time, as the tangled magnetic field lines snap and reconnect, releasing vast amounts of energy into space. As the solar cycle progresses towards solar minimum, sunspot activity dwindles, and the sun's magnetic field becomes more organized and less prone to violent outbursts. This cyclical behavior, observed for centuries through the waxing and waning of sunspots, has profound implications for Earth, influencing our planet's climate, atmosphere, and technological infrastructure. The sun, while giving us warmth and light, can unleash powerful bursts of energy, solar flares and coronal mass ejections that ripple through the solar system and sometimes impact Earth. These solar storms can disrupt technology, threaten astronauts, and create stunning auroras, reminding us of the sun's immense power and the importance of understanding space weather. The sun, our cosmic choreographer, commands the solar system with its immense gravity and radiant energy. It shapes the orbits of planets, asteroids, and comets, and sustains life on Earth through its light. Yet its dynamic magnetic field can unleash powerful storms, reminding us of its ever-changing nature and the importance of understanding our star. Despite centuries of study, the sun still holds many mysteries. Why is its corona millions of degrees hotter than its surface? Scientists suspect nanoflares and magnetic waves, but the exact cause remains elusive. The sun's magnetic dynamo and its future as a red giant are also puzzles yet to be solved. Our quest to understand the sun continues. The sun, our constant companion, shapes our planet and our lives. Its energy sustains nearly all life, drives the rhythms of day and night, and inspires wonder across cultures and time. From ancient sun worship to modern science, the sun's legacy endures, guiding our journey and connecting us to the cosmos. Its story is far from over. The sun will shine for billions of years, a beacon in our cosmic adventure. The universe is a vast and mysterious place, and there's always something new to discover, just waiting for a curious mind to come along and unravel its secrets. Thanks for making it to the end. I hope you enjoyed the video. How about hitting the like and subscribe button to be notified when we upload more videos on our cosmic wonders? And as always, stay curious and keep looking up.